Hi everyone, Mr. Ford here. Today we're going to go over worksheet 5 from the acceleration packet. Um, the answers are posted on Schoology, but I just figured it might be helpful to walk through step by step and also explain some of the nuances in either doing a solution graphically or algebraically. And there are some benefits to doing it either way as far as time or understanding, and that can let you guys decide which way you want to actually do it. Or do it both ways, and if you come up with the same answer, great. Chances are you would be correct. Um, so we already talked about question one in class, and or the one class had some connection issues, so you watched the video previously posted. Um, so here we go. So we're going to go through number two. So the first thing, making sure you're drawing a well-labeled diagram of the situation. I polled a few students few classes before, and some people were saying they did not take the time to do that. As that is definitely the way to go for the sake of time for this video and um, my lack of artistic ability. I'm not going to sketch out those diagrams. You can refer to your own diagrams, hopefully you made, and also those on Schoology. So in number two, we have a car um, that has a speed of 30 meters per second. After 6 seconds, its speed is 15, so obviously it was slowing down. So I'm going to go through and identify all the variables that are given. So our initial speed at time equals 0, so it's hinting at the start of our observation. And we know our final velocity is going to be 15, and the time that takes is 6 seconds. So hopefully we can have a well-drawn diagram labeled with those variables, maybe two different scenarios of the cars. Maybe get a little fun with it. This problem suits very well to starting off with sketching it on the velocity time graph because we don't need to do any other extra calculations or estimations, or scaling is not necessarily an issue. It's fairly easy to put these pieces of information on the graph. So we could go say, make sure we scale our graph evenly. So I'm just going to go by tens every 3 blocks. And then we're going all the way out to 6 seconds. So maybe every 3 blocks down here. Making sure I hit them evenly. So our initial velocity of 30, final of 15, which would fall someplace around here. And then we can draw our line. And then we have our graph. So what we could do next is to find the acceleration of the car. We can look at our graph and just take the slope of that line, because since it is a velocity time graph, the slope is the acceleration. So we definitely see that it's a negative acceleration, suggesting that it is slowing down because of our positive velocity that we're given. And we'll discuss that in more detail in coming classes if that kind of is a little confusing for you. So jumping over to the algebraic portion of it, to get that acceleration, we could just by definition look at acceleration as a change in velocity, or VF minus VI, over time, where we get a 15 meters per second minus our 30 over our 6 seconds. Plug that into a calculator, and we should get the same value of negative 2.5 meters per second, or meters per second squared. So whether you went and took it from the slope, a little note, if we are doing this kind of problem in a lab setting where accuracy counts, we probably don't want to be hand drawing a graph and scaling and doing some estimating of, where lines were intersect. We want to use a computer generated graph and have that computer software give us that slope. For homework, tests, quizzes, where accuracy is not necessarily important per se, hand sketching a graph and taking the slope is fine as long as we show all our work. The next part, how far did our car travel in this time? One option is to go to the graph and take the area under that line. So all of this shaded area, which I'm not good at shading in evenly, apparently. Coloring inside the lines was not my forte. And that's kind of a weird shape. So you could break that down into simply a triangle and a rectangle and add those two together and get that overall displacement. Or you could went algebraically and found that. We do have two equations that we could utilize. We can use delta x equals VIT plus 1/2 AT squared, or VF squared equals VI squared plus 2A delta x, where we're looking for the displacement, the delta x in either or. To each his own. You can pick either equation. It's up to you. A lot of times throughout the kinematics and also later on throughout the course, you'll find that there's different solutions. You can pick one equation or the other, or maybe instead of picking a more complicated equation, you could use two simpler ones. There are more than one. There's usually more than one way to solve, especially the more complicated problems that we'll come up with. So we have part one, or I rather, part I, how far does it travel? I'm just going to pick that first equation. And again, we always want to identify our variables with units. We should never be writing a number without a unit on it. And also identifying which equations we're using, so that's very clear to the observer and also to yourself when you're going back through your work. So plugging in everything, we have 30 meters per second. Making sure that we have our negative acceleration. So I'm forgetting a little bit of some of the units and some of the things here, as it is a little late at night. And this was 6 seconds. So we plug that into a calculator, and hopefully we could do that correctly, and it would spit out our 135 meters, which we would also see if we added the two areas under the lines. If they're a little off, it might be just simple scaling, not seeing exactly what those values are on a rough sketch graph. Number three, student drops a rock from the top of a 30-meter tall building. We definitely know our displacement is 30 meters. And that's the only number that is definitely apparent. A lot of times questions are not very, very clear. On a test or quiz, I would definitely specify that the student drops the rock from rest. But usually when you drop things, that's different than throwing it, kind of. So this one we can definitely assume our initial velocity is 0. I would specify definitely on a graded assignment for that. But there's also some other variables that are known but not stated. So these are usually constants. So the one constant we know here is that on Earth, everything falls with the same acceleration, 9.8 meters per second, or meters per second squared. Now we will have a conversation next class of what free fall means. Free fall technically means free of any other forces other than gravity. So this is why everything falls at the same rate. If we throw real scenarios into the mix, like dropping a brick and dropping a feather, obviously they don't drop at the same rate because there are other forces involved. But as far as this video is concerned and this homework, everything is falling at the same rate because there is no air resistance. All right, so now we have to have the discussion of direction. We talked before about like a 4-quadrant graph. But typically, I think this is how it's taught in math. So this is usually the reference frame that we try and keep so that everybody knows that up is positive, right is positive, and the other directions are negative. But sometimes we can change our view. So as if you're facing someone else or you're facing a screen, somebody on a TV screen or laptop or cell phone, your forward is their back and your forward is, wait, a little confusing. I think you get what I mean. But we can change our frame of reference. So for this one, we know the object is falling down, but there's no negative portion to our graph, right? We know that our velocity should be negative because we're going downward, but we're not given that option in this graph. So what we need to think of in advance a little bit is that we're going to define down as positive. That's okay. Why we do that sometimes is just to redirect things, and also that gets rid of some negatives. So a lot of times people think a negative acceleration means slowing down. It's not necessarily the case. But just because we're limited by that graph, we have to define our velocity, our displacement, and our acceleration all being down. So with that said, it's kind of hard to plot things. We do know the displacement. We know the acceleration. We know we're going to start at some 0 point of velocity. So to predict the area under this line and kind of figure out a scale so that we have an exact slope of 9.8 is going to be a little bit difficult to start on a hand plotted graph. So we might want to start with the algebra portion. If we're looking at computer software, we might be able to do that a little bit easily, more simply, or with a graphing calculator. So what we need to find is how fast this rock is going to hit so we can figure out our final velocity. But we don't have time, so we cannot use our first kinematic equation of VF equals VI plus AT. So we can use only one other one. It's the only equation that doesn't involve time. So that's going to be this one. So we're looking for our VF. Our VI is going to be a positive 0. So that whole term drops off. And I emphasize the positive to show that we are moving in the positive direction. For when we start to move, those numbers would be positive. And again, we are going down, so our acceleration is also going to be down, which we defined as positive. Running out of room a little bit. And we plug that into our calculator. And we get a number of 24.5 meters per second. Not forgetting to take the square root because we are looking at VF squared here, but we want to know the VF, the final velocity. So now we can kind of plot that a little bit better. And let's see how I can scale this. Let's again go every 3 is 10. I think would be good. Or every other is 5. We kind of complete our graph. Ooh, but we don't know time. So we know where we're going to plot this line, but we don't know the time at which to kind of line it up with. So then we can go back and use one of our other equations to find the time. And that's what a lot of this initial portion of physics is with these three different kinematic equations, or really we have several others with the, just general velocity, non-accelerated motion. And, sorry, bear with me. It's really a puzzle, just knowing what variables you know and what variables you need to calculate. And technically, I think as the question is kind of explained, you don't need to find the time, but that just kind of completes the graph a little bit better. So that's going to give us a time of 2.5 seconds. So seemed weird for me, sorry. I guess that's okay. So that's going to be, that's not going to work. So we'll go 1, 2, 3, 4 as 1. So this would be my 2.5 seconds, close enough. And we can plot our graph. Something about there, because 24.5 would be about there. Cool. So we have our graph. And we can move on to 4. So here we have a bus slowing down. Hopefully your picture's good. And we start identifying our variables. Now we could plot this out. We have an initial velocity. We have a final velocity. So let's start off with graphing it out. I think that kind of works well. So as long as you scale them evenly, we never ever in physics want to do this little squiggle mark thing that distorts the graph. And then also, sometimes a little bit more confusing is finding areas and things they might not visually look how they should. So we know we're going from 20 down to 0. So we're starting at 20 and we're going to end down at 0. And we need to figure out how much time that takes to pass. So we don't exactly know how much to scale our time axis for, but we could do a little bit of logical analysis. So if we know that we're starting at 20, and then for each second that goes by, we're going to slow down by 4, that should only take 5 seconds, right? Because we're going to be at 20 meters per second, and then each second that goes by, we decrease by 4. So it's 16, 12, 8, 4, and 0. So those are our 1, 2, 3, 4, 5 seconds of time going by. So we could logically think through that and then plot out our, does that work? 5 seconds, and then plot our graph, and then we could work just from the graph fairly accurately. And we logically thought through how much time, and we could take this area underneath the line to figure out how far. Hopefully some of you have noted that what this term is, the 40 meters per second each second, is the acceleration. So the acceleration is 4 meters per second per second. So for every for every 1 second that goes by, we change our velocity by 4 meters per second. Our initial was 20, and that's about all that we know. Oh, our VF is going to be 0 because we're coming to a stop. If the graph wasn't that apparent to you in seeing how much time it would take, we could use equations to solve this. Since we don't have displacement, this is our only one that we can use. Our VF was 0. Our initial velocity was 20. Identifying what the acceleration was. Which it is negative. It's a negative slope. The negative slope doesn't necessarily mean that it's slowing down. It just so happens to be that case in this problem. And also in this problem, if you look at the algebra, you'll move the 20 to the other side of the equation and just divide by 4, and you would still get a time of 5 seconds. So then how far? If we didn't want to take the area under that curve, there's 2 equations that we have. I'm just going to go with the first that we've talked about in our list. Either one would work. You'll see that in some of the equations, if there is a lot of squares or square roots, that may become a source of error for you in forgetting to press that button. So definitely always think, would this number make sense? All the physics problems that we use are real scenarios. We don't make up ridiculous, scenarios where like a human can jump 500 feet straight up in the air. So using our given quantities and our 5 seconds that we knew of, that might be something else to add. As you discover new quantities in that same problem, you might want to note them. As like this little box is all my given quantities. And we plug that all into a calculator, and it will give us a number, hopefully that's correct, of about 50 meters. Number 5, we have a car that is going from 30 to 10 in 5 seconds, so it's slowing down. So our initial, and hopefully you're now starting to see some patterns here in solving. It's really only the scenario changing and which variables we're given. This is another problem that may be a little bit easier to jump into the graph because we know that we're going 30 to 10 and we have the specific timing. So we're going to go 10, 20, 30 in 5 seconds. 1, 2. And we can go from here to 20, or sorry, 10. The acceleration we can either get from the slope or by definition of change in velocity that is not equals was so we have our acceleration. Now, with this being said, going either graphically or from the algebra, I did hand plot a graph, and it might not be clear unless I use those, quantities that I was given, like the beginning and the end. Looking at data points someplace in between, it might not be as exact. The distance that the car travels in the third second. So this we all have to kind of do some thinking. It is only from 2 to 3 seconds, and we can get distance or displacement from the area underneath. So we're only looking at this area of blocks. So where you might want to kind of sketch it out to see it's going to be a triangle plus that rectangle. And we could do that again in a equation-based form, but just making sure that we're only looking at those times. So what people have tended to do is go ahead and say, well, let's, use the displacement. Either equation would work because we have the time period, we have all the velocities, we have the acceleration. But we don't want to be using the values for VI and VF in the red equation that I mentioned below, because the scenario has changed. We're only looking for that specific time period. So from the graph, it might be easier to simply estimate these points. Let's go purple. Here and here as like 18 and 22-ish, and say our final velocity was 18 meters per second. Square that, our initial is 22. Again, these could be estimates. If we really wanted to focus in on it, we would have a computer generated graph and kind of zoom into those points. And we could solve for delta x, where delta x would be 20 meters. Which, looking back, I think I made a mistake. No, that was 50. I thought I said 20. So here we actually relied on the graph a little bit more. Could we do some algebra and use some equations to get these specific points? Sure. We can use that same equation that we kind of used in the beginning and plug in our initial velocity and figure out what final velocity we are going after the 2 seconds, and then do that equation again for the 3 seconds. But if we already have a graph, it's a lot easier just to look on it. Almost done here. Dog running down the driveway. Scenario is changing a bit. So far, we're only looking at one occurrence happening, like speeding up, slowing down, staying the same. Here we have a dog going down the driveway at a constant speed and then speeds up. So hopefully we have a diagram, and in that diagram, hopefully we're seeing that we have 2 different times. So let's see, what we don't know is necessarily how to scale this graph yet again. It's going to look something like this. Oops, if I'm on But to scale it, we might have to do some thinking logically first. So maybe it's best to start off with some algebra or some equations. So we know initial velocity is 5 meters per second, and that time is for 8 seconds. And maybe use a different color or area of your work and make a note, this is our constant velocity. Maybe let's color code it, like I said. And then when we're actually going to accelerate or speed up during the second part of it. So our final velocity for that is going to be 10, and we're going to do that for 5 seconds. So we could figure out some velocities. So I want to see where we're going here. So if we're going to be starting out at 5, and going to 10, oh, so we can kind of scale this, sorry. I was wondering why it was like so weird for me to look at. 1, 2, 3, 4, 5. So this actually works. Every block can be a meter per second. So we definitely know we're going to 13 seconds. So maybe go, I think we can go every 2 seconds for a block. And so on. We'll kind of complete it. So we're only going for 13 seconds. So the first 5, we're moving constant. Or I'm sorry, first 8. And then for another 5 seconds would be putting us at 13. We're going to accelerate to 10. And that would be our graph. So if we wanted to look at some things, if we just found this green shaded region, that's the displacement or how far the dog moved when it was going at a constant speed. The second portion is when it was speeding up. And we can kind of add them in different phases if you like. I tended to, for the whole answer, see the big rectangle and then the triangle to add together. Now, equation-wise, this is an important piece. We developed this equation before, and we briefly talked about it. But since this equation has 2 parts, the VIT part, or let's color code it better, the part that's accelerating and the part where we're moving at a constant velocity. Even though it's the same t in there, there's going to be a time where we were moving, a constant velocity, and then a time when we accelerated. So when we have variables that are the same initial, same letter, we want to add subscripts to specify, so that when we add in our data, we understand a little bit better. And I'm probably going to run out of room. Oh no. What was our acceleration? We never found that out. So we have 2 options. We can figure out the slope of that line when we're accelerating, or just a quick calculation of acceleration, pretty much by definition. where we know our change in velocity, we went from 10 or 5 to 10 in 5 seconds, I believe. Double check. Yeah. So our acceleration was only 1 meter per second squared. So not going to change a whole lot in our equation. Where we really need to focus is these times and plugging them in correctly into our calculator. And we plug that all in, and we get about 78 or so meters. Seven, physics student going down ski slope. Again, we want to call down positive here because we only have that positive quadrant to our graph. So we have the acceleration, and that's going to be positive 2. So a little note for the future, when we have velocities and accelerations that have opposite signs, like one's positive, one's negative, the object is slowing down. When the acceleration and the velocity is the same sign, whether they're both positive or they're both negative, that means the object is speeding up, increasing the speed or the velocity. So this one is a little bit harder to kind of predict and scale out because we don't know any of the terms of the axes. We do have the 15 seconds, but it's harder to estimate a slope for that without a velocity scale. So we're going to go and calculate that. So we're going to assume that our physics student is starting from rest, buckling in or waiting for friends and then deciding to go down the slope, I guess in a straight line since it's a constant acceleration. So there is another given, and we're looking for a final velocity to be able to plot it. We're not given displacement, so we can't use that in our initial, we can't use the other two equations. Oops. Now some of you are saying, Mr. Ford, if we know the acceleration, we know the time, and we understand that acceleration is for every second that goes by, we increase our velocity by 2 meters per second. And we know how long. Aren't we going to go 30 meters per second at the end? You could also make that assumption. It's a kind of a definition type equation. If you understand what it is, it's feel free to make that jump so that we could scale it. So we know we're going to start off at 0, end at 30. Let's see how I can do this. I think I do this. I think that'll work. So at 15 seconds, we'll be going 30. Plot that line in. Again, we could find the area underneath this to get the length of our slope, or use one of the other equations we were given. Like as far as the kinematic equations, that is. Starting at rest, so VIT drops to 0. Plug that all in. 225 meters. Yeah, that's kind of a big number, but it's a ski slope, so that's pretty far. It's actually small um, for a ski slope, but we weren't told the size of it. And finally, our goat going down or crashing the rocks down the slope. Same type of scenario. Again, it's just different variables that were given. We're assuming they're starting at rest. We're going to be looking for the acceleration. We could find that right in the beginning. Or we can start to figure out how to plot the graph. To plot the graph, we are going to want to know the velocity, so I'm just going to go ahead and calculate that. Or can we figure that out? All three equations had acceleration. So we actually have to find the acceleration first. So we're looking for an equation that does not have VF, because that's something we don't have. So the one equation that doesn't have VF was the one that we've been using. And again, since velocity is positive, our displacement's positive, even though we're kind of going down-ish, down the slope. And this time we're solving for acceleration instead of another variable. And that's 8 meters per second. Squared. Let's double check that's. Yeah, that's right. So we have our acceleration. We can then use that to get our final velocity, so it's easier to plot. And then we can scale that out appropriately as we see fit. So hopefully you've seen different methods to calculate the variables that we're asked to, whether it's from a graph, from algebra, or a combination of both. And these are just different tools that we're going to use. Just be sure that if you are using a graph to solve something, that you're making a statement of what you're doing. So if you're saying, oh, the acceleration is in this problem 8 meters per second, identify how you solve that. It's the slope. If it was a computer generated kind of graph, it will tell you the slope, so no need to do extra calculations. But if it's like a hand-drawn graph, you do want to show the numbers that you used, just so that there's any differences in, like a rough sketch. If you have any other questions about the homework, please feel free to let me know, and we can go over that at a later time. Have a great day.